All right, so here we are on Wednesday doing a review of Chapter 4. We're going to do some notes and some examples from Chapter 4. Obviously, many of you have seen some things from Chapter 4 and already done some problems, so I might go kind of quick, but I'm asking those of you that are live to please post up in the chat if you want more details about something, and please demand just a little bit more example problems of some things as we go along. So thank you very much for being here. Follow along, see if you can keep up. Here we go. Section 4.2 are a type of reaction called precipitation reactions, symbolized PPT. It's one of the three types or broad categories of reactions that Chapter 4 talks about. The broad categories are precipitation reaction, acid-base reactions, and redox reactions. And you can pretty much classify most all reactions, not all, but many different reactions into those three really broad categories, and we'll focus on precipitation reactions first for about 5 minutes. Precipitation reactions means that you're going to form a solid. So some people call them solid forming reactions, and so you're going to have something that's aqueous on this side plus something that's aqueous on this side, and then it's going to form a solid or a precipitate on this side. Precipitation reactions are ones that you usually write as what are called net ionic equations, because when things are soluble or aqueous, many of them are strong electrolytes, and so you split those up into their ions, and then you bring them together if they're a solid on the other side. To figure out if they're going to be a solid, you need your periodic table, and you need these solubility rules right here. And the mainly water solutions are listed here on the top with all their exceptions, and then some insoluble things are down here. Some of the tricky ones that people don't get are these right here, group 1. Group 1 are all of these elements right here. So if it's got one of those in it, it's always soluble. So that's an easy one to get right away. It's just a matter of they don't list all those elements here, so a lot of people write them in here. Lithium, sodium, potassium, rubidium, cesium. All right, so let's do one of these kind of reactions with a net ionic equation. I'm going to go to this guy right here, sample exercise 4.4. I'll try to zoom in just a little bit more on there so you can kind of read it on the screen, or you can pull it up on your book too. Sample exercise 4.4 says, write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of calcium chloride, tells us it's aqueous, so we put a little AQ down below it, and sodium carbonate are mixed. So plus sodium carbonate, make sure you put a 2 down here because carbonate's -2, sodium's +1. Arrow on this side. Now these are also called exchange reactions. Some people call them double replacement reactions. The fancy name for them are metathesis reactions, and this means that you swap the cations. So you swap those two guys, and then you get Na together with the Cl right here. Make sure that you get the charges for them from the periodic table. Sodium is +1, of course, and then chlorine is -1, so +1, -1, 1 below each one of those. And then there's going to be calcium together with the carbonate. So calcium, +2 charge. If you look on your periodic table, here's the calcium, and then carbonate is right here on the right-hand side. Look on the back of the periodic table if you forgot the charge, and carbonate is -2. So since it's +2 and -2, you don't need any subscripts on there as well. All right, that's step number 1. That's the balanced reaction, and now you have to, the skeleton reaction. Now you have to balance it. So we've got 2 here for sodium, so I'll need a 2 here. That gives me 2 chlorides. Now the reaction's balanced. They tell us that these are aqueous solutions in the question, aqueous solutions of calcium chloride and sodium carbonate. So those two I don't have to look up to see if they're going to be soluble or not. But on the right-hand side, I've got to look up both of those. So look over here, and you see right away all chlorides are soluble except for silver, mercury, and lead. This is not silver, mercury, and lead, so this one will be aqueous. And calcium carbonate, if you look under here, all carbonates are insoluble except for the 1A elements in ammonia. Well, the 1A elements are not calcium. Calcium's in the 2A, or the group 2 right here. So this is going to be a solid precipitate. So that's my solid that forms. That's step number 1, just deciding what happens, writing the balanced skeleton equation. Step number 2 now, we have to go through and decide whether to split them up. Are they strong electrolytes? Well, calcium chloride is. because it's an aqueous salt, so split it up into Ca plus 2 and 2 Cl minuses. Sodium carbonate splits up into Na plus 2 and CO3 2 minus. Notice how the 2 went out front of the sodium and the 2 went out front of the chloride because they're ions now, and they're not, this 2 is only here because calcium is plus 2, but we know that when it breaks up, there's going to be 2 of those ions. On the right-hand side, NaCl right here is aqueous as well, so write it as 2 Na plus and 2 Cl minuses. And then this guy is a solid, so we don't break it up, so leave it together as CaCO3. Be really careful about writing the charges and be really particular and picky about those. Notice anything on both sides of the reaction can cancel, so those will cancel, and then we're left with 2. Whoops, I'm sorry, I crossed off the wrong thing. The Na right here goes away. This is still there. So we're left with Ca plus 2 and the CO3 2 minus, and on the right-hand side we have CaCO3. So there is our complete molecular equation. There is our ionic equation, the complete ionic equation, and this is what's called the net ionic equation. And when you write these, you can go ahead and drop the aqueous and the solid things, because if it's aqueous, it's going to have a little charge up here. If it's a solid, of course, it's just going to be all together at once. Any questions about the solid precipitate forming net ionic equation writing ones? Is that enough of a review? Do you want me to do more of those? Do you want me to talk about those kinds of reactions more? Please post up in the chat a yes or a no. All right, nobody wants to know any more about those. So we'll go on to the next part. I'll put a poll up for the next one, and we'll see what your confidence ranking is. Section 4.3 is the second type of reaction. These are called acid-base reactions. Now, acids, if you remember, are things that donate hydrogens or give away H's. Bases are acceptors of hydrogens. And so when you're writing acid-base reactions, always look for the acid to give away the H. Always look for the base to have one more H than it had to start with on the right-hand side. Or the products side of the reaction. There are 7 strong acids that you memorized and had to give a quiz to, and there are 8 strong bases that you had to memorize and give a quiz to as well. Here are a number of them listed right here on this page, and the important part about them being strong is that they fully dissociate or break up or ionize. And so when you're writing a net ionic equation with them, those will be ones that form ions like this. They don't stick together like calcium carbonate. So that's what's important about the strong ones. Let's see, a couple of special ones that you should know. I know a couple of these show up on the test are the gas-forming acid-base reactions. So the gas-forming ones are ones where an acid reacts with something and it forms a gas on the right-hand side. The gas-forming ones are ones that have a carbonate in them, a bicarbonate in them. This would be -2, this would be -1. Sulfite or a bisulfite, or some people call it hydrogen sulfite. The other one that forms a gas is if you're with a sulfide, and then these are going to form gases of either carbon dioxide from these two guys. These guys will form sulfur dioxide, and this will form H2S gas right here. You can see these reactions right here on page 138, and they do a number of these gas-forming reactions. Here's one with sulfur right here. Here's one with the bicarbonate, or the HCO3. You notice right here that it forms carbon dioxide gas because that decomposes. And then, let's see, they show another bicarbonate one right here too. I know there's a couple on there with the gas-forming pieces. Give me a confidence ranking on this poll. Okay, confidence ranking on this poll as far as how good you are at acid-base reactions. 5 super confident, 4, 3, 2, 1 not so super confident. Okay, so we have a number 3, 4s, and 5s, so I'll probably come back to that if you want more of those acid-base ones. I can come back to this one at the end, but there's a lot to cover in this chapter, and I'm going to get on to the next type called oxidation-reduction reactions. And if you want to see some acid-base ones a little bit later, you sure can. The third type of reaction are called oxidation-reduction reactions, or some people call them redox, for reduction and oxidation reactions. So oxidation is the loss of electrons, reduction is the gain of electrons, or I like to think of it that things go up in charge if they're oxidized, and things go down in charge if they're reduced. Down and reduced both start with consonants, up and oxidized both start with vowels. So number one thing you have to be able to do is assign oxidation numbers to determine if a redox reaction is happening. And the rules for assigning oxidation numbers are on the bottom of page 140 and the top of page 141. I also outlined them in great detail in a video cast that you guys watched before. Here's just a few of the rules. I'm going to put them on the right hand side, and then I'll do an example problem of assigning oxidation numbers to decide whether a reaction is redox or not. So rule number 1, if something is in its elemental form, then it has an oxidation number of 0. So if it's Br2, if it's Fe, if it's just one of those kind, then it has an oxidation number of 0. A monatomic ion is its charge. So if you see Cl minus 2, Cl minus 1, S minus 2, this is a minus 1 charge. This is minus 2. So if you see it in an ionic equation or a net ionic equation and it has a little charge up above it, then that's its charge. A couple of general rules on the periodic table are that when things are in compounds from group 1, they're plus 1. When things are in compounds from group 2, those things are plus 2. Aluminum is always plus 3, zinc is always plus 2, cadmium is always plus 2, and silver is always plus 1. Those rules that you learned back in chapter 2 still hold true. And so, you know, plus 1, plus 2, 3, 2, 2, 1, those hold true 99.9% of the time. Over here, things get a little bit fuzzier. These guys are minus 1 when they're with metals. But when they're with nonmetals, their oxidation numbers can change. These guys are minus 2 when they're with metals, but when they're with nonmetals, their oxidation numbers can change. These guys are minus 3, but when they're with nonmetals, their oxidation numbers can change. A couple other rules. Rule number 3, hydrogen is positive 1 when it's with nonmetals. Hydrogen is negative 1 when it's with metals. Fluorine is always negative 1. This is one you can be assured of. That one's always true. You don't see that very much in this, but here's an always. All the other ones are kind of variable. Oxygen is usually minus 2. There's a couple of exceptions. When oxygen is the peroxide ion, like this, O2 minus 2, peroxide ion, you can find that ion on the back here, then each one of these oxygen atoms in here is negative 1. Last rule, rule number 4, is called the sum rule. Sum rule means that if you add up the oxidation numbers in a species, it always equals whatever that oxidation number's charge is in the upper right hand corner. So for example, SO4 minus 2, whatever sulfur's oxidation number is, plus whatever 4 oxygen's oxidation numbers are, has to add up to negative 2. Because there's a little negative 2 up in the upper right hand corner. If it's CO2, just the compound CO2, well, it doesn't have any number in the upper right hand corner. So whatever carbon's oxidation number is, plus whatever 2 oxygen's oxidation number is, that has to add up to 0, because there's no number in the upper right hand corner. If there's no number, just assume that it is 0. All right, let's go through and let's assign some oxidation numbers, and let's see if a reaction is redox or not. Let's find one on here that's kind of tricky. Here's a good one down here. Let's just use this reaction that happens to be on this page. This one is Cu plus 4HNO3 arrow, and then Cu, and then NO3 2, and then it has 2H2O, and then it has 2NO2. Let's take this reaction. I'll write it on a new piece of paper so it's a little bit bigger, and then we'll assign oxidation numbers to everything on this side. We'll assign oxidation numbers to everything on this side, and we'll decide who's oxidized, who's reduced, and of course, if it's an oxidation or reduction reaction, then we'll have one of each of those things going on. So give me a second, I'll get another piece of paper. And I'm going to rewrite this reaction way up here at the top. So Cu plus 4HNO3 plus, oops, it's an arrow now, sorry, copper nitrate over here, 2. And then we've got 2 waters. And lastly, we got 2 NO2 gases over here. I took this reaction from page number, what is that, 144, if you were following along in your book. All right, so let's apply the rules. Rule number 1 says that it's an element in its elemental form. Its oxidation number is 0. Okay, so copper is 0. Right here, we've got 3 elements in this. This is kind of tricky, so here's kind of a sneaky way to do this. Hydrogen is with a bunch of nonmetals. Nitrogen and oxygen are both nonmetals. Nitrogen and oxygen over here are both nonmetals. So that means if hydrogen is with nonmetals, it's going to be +1. Okay? I've seen NO3 before. As a matter of fact, you probably memorized NO3 on this side. And that polyatomic ion is -1 overall. And so this boxed in species right here, this part is -1. I can take and break this up. And I could say, okay, what is nitrogen inside of this? And what is oxygen inside of this? So oxygen I know is -2 almost always, except for in the peroxide ion. There are 3 of them in this formula, or in this polyatomic ion. I know it's got to add up to -1 because I know nitrate is -1 in the side of this compound. And nitrogen would then have to be some charge, and I don't know what it is, but when I add it to -6, it's got to end up being -1 total. So that means nitrogen's got to be +5 in this case. So nitrogen's +5 over here, oxygen's -2. Now let's go to the right-hand side and we'll see if anything changes. If nothing changes, then it's not a redox reaction, and it would either be an acid-base or it would be a precipitation reaction. So let's start right here on this side, and let's go with oxygen is -2. There's no number in the upper right-hand corner here, so whatever nitrogen is plus 2 times whatever oxygen is has got to add up to equal 0. So something plus -4 equals 0. That means nitrogen's got to be +4 over here on this side. Notice I ignored the coefficient right here because the coefficients have nothing to do with assigning oxidation numbers. But now I notice that nitrogen changed. It went from +5 to +4 on this side of the reaction. This change is where it went down in charge. Something goes down from 5 to 4, we say that it is reduced. So my species that underwent reduction is my nitrogen, my species that is reduced. Let's continue over here. Oxygen is -2, hydrogen's +1, +1 plus times 2 plus -2 adds up to 0, which is another way to check it. Notice I ignored this 2 right here. Copper nitrate, okay, let's see. Let's use the trick again. Nitrate right here, I've seen that before. I know that's -1. I memorized that on a periodic table. There are 2 of them inside of here, so whatever copper's charge is plus -2 has to add up and equal 0 because there's no number in the upper right-hand corner here. So that means copper must be +2. All right. I could go through and I could assign oxidation numbers to the nitrate, but it's going to end up being exactly the same as over here. So my nitrogen's going to be +5, my oxygen's going to be -2 just like before. But I've now identified my other species that changed. Notice how copper went from 0 to +2. Copper went up in charge, and things that go up in charge are said to be oxidized. So my oxidized species is copper. So here's an example of how to determine whether a reaction is redox or not. Assign all the oxidation numbers, decide which thing went up in charge, that's oxidized, decide which thing went down in charge, that thing is reduced. How are we on the oxidation reduction after that. All right, there's a new poll open now. What's your confidence ranking in doing redox reactions? 5, 4, 3, 2, or 1? Okay, so it looks like we have a little wider range here. We have a 2, a 3, a lot of 4s and some 5s. So we're pretty decent on that. Maybe that's another thing that if you want to hang around after I go through the molarity part and the stoichiometry part, you want to ask another question on that, or on the acid-base reactions, you're more than welcome to do so at the end. So after those 3 types of reactions, now Chapter 4 changes course to a little bit more mathematical piece, and they change to, sorry, we're not going to let you annotate right now. Anyway, it changes course to, if you do have a question, go ahead and post it up in the chat. Anyway, to a little bit more mathematical part, and since this is called reactions in aqueous solutions, they talk about concentration. And concentration is measured in a unit called molarity. And molarity is equal to moles divided by liters. And I always write it as a triangle like this, where molarity is equal to moles divided by liters. If you want to know moles, take molarity times liters. If you want to know liters, take moles and divide it by molarity. So this is always liters of total solution, and this is always moles of the solute. That's the thing that's dissolved in the solution. So if you take copper sulfate and dissolve it in water, the copper sulfate would be the solute, and then the liters of solution would be both those things added together, which is usually just the volume of water that you're dissolving it into. So molarity equals moles of solute divided by volume of liters in solution right here. All right, there's a couple of different types of problems that they have for molarity in here. I think I'll do a dilution problem, just because that's one that is usually confused on the test, and people are okay with this because they've seen molarity before, but dilution is one that tricks people. So dilution means that you have a solution. There's probably a picture in here. Yeah, here we go. We have a solution, and then we take a certain amount of it out, and then we add water to it. And you can maybe even tell that this one's a little bit more clear than this one. And so when you add water to something, you are diluting it by having less of the moles of the stuff in there were before. So the moles from the initial solution to the moles of the final solution remain the same, because after you take some of this out and put it in here, the moles of this went into here. But what you're adding to it is water. And so what you can do is you can write this equation in another way. You can solve this for moles, and you can say that's equal to molarity times liters, so molarity times volume. And then you can solve this for moles, and that's molarity times volume again, so molarity times volume. And you usually put a 1 below these and a 2 below these, and so it's a M1 V1 equals M2 V2. Some people call it the dilution equation. So here's a preparing a solution by dilution sample exercise. This is sample exercise 4.14 in your textbook, and it asks how many milliliters of 3 molar H2SO4 are needed to make 450 milliliters of 0.1 molar H2SO4. So step number 1, I always like to write down my data. So I have 3.0 molar H2SO4, and that's to start with. So that's my initial molarity. And then we're going to make 450 milliliters, so that's my final volume. I'm going to make 450 milliliters of it. And then eventually I want it to be 0.1 molar right here, so my final molarity is going to be 0.10 molar. So that's my data pieces. Now I can plug it into this equation. My initial molarity, I'm going to find out how much of this initial molarity I'm going to need. So 3 molar times my initial volume that I'm going to need is equal to my final volume. And as long as the units match, I can use milliliters in here. Just know that my volume is going to end up being in milliliters here. And find my final molarity is 0.1 molar. Notice my molarities will cancel with each other because I'll end up dividing by 3 molar on both sides. And so I'll end up with my answer in milliliters. So 450 times 0.1 is 45. 45 divided by 3, I think that ends up being 15 milliliters. So this tells me that I'd need 15 milliliters of this 3 molar H2SO4, and then the rest of it I'd have to add to it as water. And so that might be a follow-up question, is how much water has to be added to make this happen? Well, you have 15 milliliters of this. You need 450 milliliters total, so 450 minus 15 would give you the amount of water that is added to it. All right. Confidence ranking in doing concentration or dilution type problems. Confidence ranking on those. All right, we're all 3, 4s, and 5s on that. So if you want more, remember, just stay a little bit later. Let's go on to the last part. This is solution stoichiometry, section 4.6. So in solution stoichiometry, you do the same 4 steps that you learned in stoichiometry in chapter 3. Start with the balanced chemical equation. Step number 2, convert to moles. The only thing that changes here now in this one is that you have this guy to help you convert to moles. And so you not only have these ways to convert to moles right here, but you also have this thing to help you convert to moles. So that's what makes it tricky. If it's got 2 reactants or more, then you have to divide by the coefficient to determine the limiter. The mole-to-mole ratio remains the same. And then step number 4 becomes trickier too, because you have this guy right here. You might be asked to find a concentration, or you might be asked to find a liters of solution at the end. And so that's what makes the solution stoichiometry trickier than the regular stoichiometry. So I have a series of example problems that I'm going to work through. And if you've got questions on those problems as we go along, I'll keep these steps right up here and I'll follow those along as we go through them. So my first one is sample exercise 4.15. I'm going to work that one, and then you can ask questions along the way for that one or the next ones. 4.15. This is on page 152 in your textbook. How many grams of CaOH2 are needed to neutralize 25 milliliters of 0.1 HNO3? CaOH2 neutralizing HNO3. Step number 1, balanced chemical equation. So I've got my HNO3 and my CaOH2. Looks like an acid-base reaction to me. This is a strong acid and a strong base. So swap the cations. I'm going to get calcium together with the nitrate. Calcium's positive 2. If you forgot that, look on your periodic table. Notice that calcium's in the group 2 right here. Nitrate's on the back, and you memorized nitrate's -1. So make sure that you have a 2 down here for that. And then the H goes with OH, so I end with some HOH over here, because hydrogen's +1, hydroxide's -1. All right, balance the equation. I need a 2 right here, and I believe I need a 2 right here, and then I think it's balanced. Step number 1 is done. Step number 2, convert to moles. Well, we're given some data here about HNO3. We're told that we have 25 milliliters of this, and we're told that it's 0.1 molar. Well, I just learned this thing. Molarity equals moles divided by liters, and if I know my liters, which I can find from here, and if I know my molarity, well, then I can find moles. So that's my species that I can go ahead and convert to moles. So let's go ahead and do that. 0.1 molar times, convert this to liters, so 1, 2, 3 to the left is 0.025 liters. That are my number of moles that I will have in step number 2. I'm just going to stop right there and not do it on the calculator until the end. Okay. Next, I'm going to put the units in there though. HNO3. Step number 2.5, divide by the coefficient to determine the limiter. Well, I'm only given information about one of them, and it's actually asking about how much CaOH2 I'm going to need. And so I don't have to worry about it being a limiter in this particular problem because it doesn't give me data about both of them. Step number 3 is the mole to mole ratio. So now take HNO3 and put it in a position where it's going to cancel. Take calcium hydroxide, the thing that I want to know, my desired units, and put that on the top. I desire to know this. If I go back and reread the question, it says how many grams of CaOH2. I can't get to grams yet, but I can get to moles of CaOH2 from moles of HNO3, because remember these brackets right here give me moles. Molarity times liters equals moles, so those are going to cancel with each other. All right, mole to mole ratio then from the balanced chemical equation. CaOH2 has a 1 in front of it, HNO3 has a 2 in front of it. And then it says convert to the asked for units. Whoops, I should have put another multiply sign here because I can do the last step. So I go back and reread the question, and what does it want to know? It wants to know grams of CaOH2. So put a multiply sign, put a line right here. Put your desired units on the top, grams of CaOH2. And then put the units that you have in a position where it's going to cancel, and that's moles of CaOH2 from right here. In 1 mole of CaOH2, I've got to add that up on the periodic table. And I think that adds up to, I'm going to peek on here, 74.1 grams. So now on your calculator, if you want to try it, take 0.1 times 0.025 times 1 divided by 2 times 74.1. I'm going to cheat and look at the book answer here. It says you should end up with 0.926 grams to 3 significant figures of CaOH2. All right, did you see all the steps? 1, 2, 3, 4, convert to the asked for units. Tricky part of converting to moles this way. All right, I'm going to go on to a second example now. Uh-oh, stay back here. So let's do this one, 4.16. This one is called a titration, and a titration is simply a way of determining an amount or a concentration of something by neutralizing it or adding an opposite amount to an opposite amount to the opposite species. So, for example, many titration experiments are what are called acid-base titrations. So if you have an acid, you would add a base to it, and you would say, like, what concentration of this is. So titration we'll actually do a lab with. It'll be a virtual lab, but we'll do one after this next chapter. So let's read this one right now. Sample exercise 4.16. It uses these same steps right here. One commercial method used to peel potatoes is to soak them in NaOH solution for a short amount of time and then remove the potatoes and spray off the peel. The NaOH concentration is normally 3 to 6 molar, and the solution must be analyzed periodically. In one such analysis, the NaOH solution, there are 45.7 milliliters. Notice how I write it down, and I write down my data right away, of 0.5 molar. In one such analysis, 45.7 milliliters of 0.5 molar H2SO4 is required to neutralize 20 milliliters of the NaOH. So it says we're going to take H2SO4 then and titrate it or neutralize the NaOH with that. What is the concentration of the NaOH solution? So we want to know the concentration of this guy right here. And we're told some data about the H2SO4. We're told that there are 45.7 milliliters are needed to neutralize it, and it is 0.5 molar. So step number 1, write the balanced chemical equation. So you have to decipher all of that story about potatoes down to being NaOH being titrated or neutralized with H2SO4. Acid-base reaction, swap the cations again. We get Na together with SO4. Remember that Na is +1 and sulfate is -2. Na, remember, is in group 1. So make sure that you have a 2 down here for that. And then the H and the OH go together. And then to balance this, I think we're going to need a 2 right here and a 2 right here. All right, ultimately it wants to know this concentration right here. It wants to know this molarity because it wants to test and see, is the NaOH good enough to peel some potatoes in the future. So step number 2, convert to moles. Look at the data that you're given. Do you have enough data for either one of these to convert to moles? And if you remember your molarity triangle, you'd know that if I have the volume and if I have the molarity, I could convert to moles. This one, I ultimately want to know the molarity, but I don't know enough data right now to find it. So convert to moles right here, 0.5 molar times 0.3 to the left, 1, 2, 3, 0.457 liters. And this would give me my moles of H2SO4. So step number 2 is done. Step number 3 then is the mole-to-mole ratio. So we'll take and we'll put H2SO4, the units that I have, in a position where it's going to cancel. And then we'll put NaOH as my new set of units because that's my desired species that I want to know. I want to know the NaOH solution's concentration. So we'll put that right up here. And these are moles once again for each one of them because molarity times liter right here gives me moles. So the moles will cancel with the moles. So in front of H2SO4 there's a 1. In front of NaOH there's a 2. That finishes step 3. And now in step 4 I need to convert to the asked for units. And what I need to know is molarity. And if I stopped right here and hit the buttons on my calculator, I'd have moles of NaOH. And if I want to know the concentration of that, the molarity, it's equal to moles divided by liters. So I'd take this number and divide it by the liters of NaOH that I used as a sample, which was 20 milliliters, or if I go 1, 2, 3 to the left, it's 0.020 liters. So let's try that on a calculator once, and let's see what we get for an intermediate answer. 0.5. You can watch my calculator, make sure I don't make too many mistakes. Try it on your own, please. 0.0457. Enter. Multiply that by 2. Enter. Divide by 1. So this is my number that goes right here, 0.0457. And now I'm going to divide that by 0.02. And I end up with 2.285. And that would be my molarity. Let's check. Did I get close to what it says in the book? .28. I got 2.285. All right. Confidence ranking on doing these types of solution stoichiometry problems. Not the limiting reactant ones yet, because I'll do one of those next, but how confident are you on these kind that are the non-limiters, might be called titration ones? What's your confidence ranking? Woo, we're pretty confident in those. Good job. All right, let's go to the limiting reactant stoich ones now. Last thing today, and then I'll go back to talk about whatever anybody has more questions about afterwards. So this is on page number 155, and this is the sample integrative exercise, putting things together from past chapters, and of course it's going to put together limiting reactants. So sample integrative exercise, page 155. It's a long, challenging problem that's got limiters in it and a few other questions as well. All right, so this one says, I'm going to take it, I'm going to turn this sideways so we can see the whole problem, hopefully. There we go. Okay, so this says, a sample of 70.5 milligrams of potassium phosphate is added to 15 milliliters of 0.05 molar silver nitrate, resulting in the formation of a precipitate. Ooh, a precipitation reaction type question. Yep. Write the molecular equation for the reaction. So it's going to ask us to do step number 1, write the balanced chemical equation. So potassium phosphate, I know that phosphate is -3 because I memorized that. I know that potassium is +1 because it's in group 1, so I'm going to need a 3 here. And then it's added to silver nitrate. So silver nitrate is AgNO3. Silver's +1 because silver's always +1. And then nitrate is -1, so it's NO3. Arrow going to the right, swap the cations. They call it a metathesis reaction, remember? K goes here with the NO3. Potassium's +1, nitrate's -1, so that formula is okay. And then silver together with the phosphate. So Ag and then PO4. Silver's +1. Phosphate's -3, so that means I'll need a 3 right here. Balancing this reaction then, I think I need a 3 here. It gives me 3 nitrates, and I need 3 potassium, so I put a 3 right here, and I think that's the balanced chemical reaction. Step number 2, when in doubt, convert to moles, and I'm given 2 things that I can convert to moles, so I'm going to have to do 2 of them and then go on to step 2.5. So the first thing I'm going to do is take my potassium phosphate, and I'm going to convert that to moles, and I'm told that I have 70.5 milligrams, which if I want that in grams, I've got to go 3 to the left. 1, 2, 3, so 0.0705 grams of the K3PO4, and then I'm going to convert that to moles. And then my second thing that I know enough about to convert to moles is AgNO3, and I'm told that I have 15 milliliters of 0.05 molar, so using the molarity triangle, 0.05 molar times the liters, so 3 to the left, 1, 2, 3, 0.015 liters of the AgNO3. That should give me my moles of that. So let's add up K3PO4 on the periodic table. I'm going to cheat, and I'm just going to use what the book has for it. So grams of K3PO4 is 212.3 grams when you add up 3 Ks, 1 phosphorus, and 4 oxygens on the periodic table. And that's 1 mole of the K3PO4. How did I know how to do that? Well, some people forget that we learned how to do that back here. We had grams and we went to moles. So we put 1 mole on the top, put the molar mass on the bottom. So that's how we did that. And then in the bottom right here we have 0.05 times 0.0105. And let's see, I think we get 7.5 times 10 to the -4th moles of the AgNO3. And then up here, taking this number divided by 212, we end up with 3.32 times 10 to the -4th moles of the K3PO4. All right, so we're just step 2.5 now. We did all the converting to moles. We have moles of this, moles of this. Now we have to divide by the coefficient to determine the limiter. Remember, we don't actually have to do the division. We just have to decide which one would be smaller. So the AgNO3 would be divided by 3. The K3PO4 would be divided by 1. So which number would end up being smaller? Well, 3 divided by 1 would end up being 3. 7.5 divided by 3 Well, I think 7.5 divided by 3 is going to end up being a little smaller than 3.3. As a matter of fact, it's going to end up being 2.5 times 10 to the 4th. And you can go ahead and try it on your calculator just to decide which one's going to be smaller. And now I know that this one right here, the smaller one, this one after dividing by the coefficient, would limit the reaction. Any questions on how I determine the limiter? Okay, so the limiter, remember what I did was I found the moles, then I divided by its coefficient, and whichever one ended up being smaller after I did the division, that one is the limiter. Now I work the rest of the problem based on those steps. And the question says, I have to go back and reread it, what is the limiting reactant? We got it. Then letter C, calculate the theoretical yield in grams of the precipitate that forms. So the precipitate that forms is going to be one of these two guys. I probably should have looked that up first when we were writing the reaction. But KNO3, will that be soluble or not? Will that form a precipitate? Well, remember, alkali metal cations are all soluble, and of course all nitrates are soluble. So this is going to be aqueous. So my precipitate must be this guy, and lo and behold, all phosphates are insoluble except for group 1. Silver, of course, is not in group 1. It's right here. And so this is going to be my precipitate or my solid. So this is the thing that I want to know for question letter C. How many grams of that will be produced? So step number 3, I take my limiter, and I write that down, 7.5 e to the negative 4th, and that's moles of AgNO3. Put a multiply sign, put a line. Put AgNO3 in a position where it's going to cancel because that's my known units. And now put my desired units on the top. The thing that I desire to know is the silver phosphate up here, Ag3PO4, because that's going to be my precipitate, and it asks what grams of that precipitate will form. There's a 1 in front of this guy. There's a 3 in front of this guy, so put a 3 down here. And I can go to the last step, convert to the asked for units. If it just asked for moles of it, I'd be done, because this is a mole to mole ratio right here in the balanced chemical, or in the mole-mole ratio, step 3 right here. But it asked for grams at the end. And so I'm going to do the last step of going from moles of the Ag3PO4 to grams of the Ag3PO4. And that, of course, I have to do from the periodic table to go from moles to grams. Molar mass on the top, 1 mole on the bottom. So 1 goes down here. I have to add up Ag3PO4 on the periodic table, and I'm going to cheat on this. It's 418.7 grams when you add up 3 silvers, 1 phosphorus, and 4 oxygens. And now try it on your calculator, and let's see how we do. Let's see if we match. Let's see if we did everything right. First of all, 7.4, enter exponent, negative 4th, and then divided by 3, enter, I'm getting really fuzzy, there we go, and then times 418 times 418.7. Enter. I got decimal point 103. I'll round that 3 grams. I'm not sure. I think it's 3 sig figs we go to, but that should be. Let's look at the. Oh, they got 0.1 grams. It's to 2 sig figs, and I have 0.10 right there. So 0.10 grams of Ag3PO4. All right, that was a long problem, difficult, challenging. Here we go. Let's see if we can do it. What is your confidence ranking in the solution, stoichiometry, limiting, reactant type difficult, challenging problems like this? All right, looks like we're 2s and 3s, a few 4s on that. I'm going to open it up now. This is almost an hour, and I promised that I'd open it up for questions. Maybe list up in the chat which thing you'd like me to do next. Would you like me to do another solution stoichiometry limiter reactant problem like this? Would you like me to go back and talk about redox reactions? Would you like me to go back and talk about acid-base reactions? Those were the three that people seem to have the most confidence type questions on. So post it up in the chat privately if you don't want to post it up to everybody, but I'll go by what the consensus asks for. So post something up and then I'll pick something to work. Okay, I have two requests for another limiting reactant stoichiometry problem. So I'm going to get another piece of paper and we'll just make one up and we'll work one. And it'll be we'll do one with limiters as well. If you're got enough information for the day, you're welcome to tune off. If you want to watch the stoich one, you're more than welcome to stay too. So this is another limiter, and we'll make it be solution stoich. Okay, so let's pick a balanced reaction that's already done for us. So let's take something like nitrogen plus hydrogen makes NH3. This is the production of ammonia, and let's make it tricky, and let's just say that this isn't really true, but we'll just make this up. We'll say it's aqueous, and we'll ask the question like, what is the liters of this that are produced if it's let's make it easy, 0.5 molar at the end. And then let's say that we're given 10 grams of this one, and I don't know how this would work, but let's just make it be solution stoich. This is made up once again. Let's say this is aqueous, even though it never would be. Let's pretend that this is 0.1 molar, and we have let's say 100 milliliters of it. Okay? So in word form, it would say how many liters of aqueous ammonia can be produced if we're given 10 grams of nitrogen and it's reacted with 100 milliliters of 0.1 molar H2. So we're given an amount of both of these, and we want to know how much of this in liters can be produced if it's this concentration. Step number one, write the balanced chemical equation. So this isn't balanced right now. We need a 2 here, and then that means we need a 3 right here. Step number 2, convert to moles. So take our 10 grams of nitrogen, and we're going to convert that to moles, and take our hydrogen right here, which is 0.1 molar, and we'll multiply that by liters. Remember, 1, 2, 3 to the left would give us 0.1 liters right here. 0.1 times 0.1 is 0.01 moles. Nitrogen, you have to look this up on the periodic table and go from grams to moles. So look on your periodic table right here for nitrogen, and nitrogen is 14, and there's 2 of them, so that's 28 grams in a mole. So 10 divided by 28, I get 0.357 right here. Okay, that's my number of moles of nitrogen. All right, and this is my moles of hydrogen right here. So then let's go and let's do divide by the coefficient to determine the limiter. So the coefficient in front of nitrogen is 1. The coefficient in front of hydrogen is 3. And maybe this one is really obvious. Which one's going to end up being the smallest? Well, obviously this guy's already smaller, and you're going to divide it by 3, so it's going to be even smaller. So this is my limiter. All right? Now work the rest of the problem based on the limiting reagent. So rewrite your hydrogen, 0.01 moles of hydrogen, and put a multiply sign, put a line. Take your desired unit, ammonia right here, and put it on the top, and H3. Take the units that you already know, H2, and put it in a position where it's going to cancel. For every 3 hydrogens, there's 2 ammonias. So this would give me moles of ammonia right now. And the savvy chemistry student recognizes that, hey, if I know moles and if I know molarity, right here. If I know moles and I know molarity, guess what I could find? Well, I could find my liters right here. So knowing that molarity triangle will help you find liters is critical in this part. So 0.1 times 2 divided by 3. Whoops, I'm sorry, it's 0.01 times 2, enter, divided by 3, enter, gives me 6.66, repeating, times 10 to the negative third moles of NH3. Now I can take that moles, divide it by the molarity, and it says it's 0.5 molar, and that should give me my liters. So take this number, divide it by 0.5, and I end up with 0.01333 repeating liters. And if I'm not worried about sig figs, I'm done. If I'm worried about sig figs, look back at the data that I'm given. Oh, it looks like I'm given only one sig fig when I made up this problem. So let's just leave the answer at that. Anyway, notice the steps. That's the important part of this, the steps that we did. Even though we made up a lot of things in this one, notice the first thing we did was balance the equation. Then we took our data and we converted each to moles. Then we divided by the coefficient right here to determine the limiter. And then we used the mole-to-mole ratio using our limiter to determine what would be produced. And then lastly, we converted to the asked for units using the molarity triangle right here. All right. Other questions before signing off? Homework problems or problems from something else? Any other ones? Okay, so let's see. We have a question about problem number 52C. So let's take a look at that one, 52C right here. Oh, and assigning oxidation numbers problem. Oh, this is a tricky one. This is a good one to ask about. All right. So let's rewrite this one down here, 52C. So this is CH3CH2OH. And then we have 3 O2. And then on the right-hand side, we have 3 H2Os. And then we have 2 CO2s right here. All right, so let's take the easy ones first. This would be easy, right, because that's 0. And it doesn't make any difference if it's solid, liquid, gas, aqueous. It doesn't make any difference, and you don't have to pay any attention to the coefficients either. You just have to go through and use the rules to assign the oxidation numbers. So go through and just pick out the easy ones first, remembering that the easy ones are probably like oxygen. Hydrogen with a non-metal is going to be +1, which means this oxygen is going to be -2. Oxygen here is -2 almost all the time. 2 times -2 is -4, which means this carbon is going to have to be +4, right? And then over here on this side, this is a tricky, mean one. But what helps sometimes is to put all these together. So you could do the whole formula is actually C2 because there's 2 carbons. There's 5, 6 hydrogens together, and then there's 1 oxygen right there. And so it helps sometimes to put them together so you're not figuring out so many things. And then you can go with your simple rules of oxygen's usually -2. Hydrogen is with nonmetals now. Nonmetals are, carbon, hydrogen, oxygen. So that means it's going to be +1. And now we need to do a math problem, and we're not going to like this math problem because some number times 2 plus +6, right, because there's 6 of these plus 1s, plus -2, and it all has to add up to equal 0. So this part right here would be +4. So something times 2 plus +4 is equal to 0. That means carbon in this case must be -2. Did I do that math right? I think I did that right. 2 +6 times 2 +4. Yep. So that means carbon goes from -2 to +4, and so that goes up in charge and it's oxidized. And then oxygen right here goes from -2 to 0 right here. Oh, that one looks like it goes up as well. I must have made a mistake on this one. What did I do wrong? -2, this one up. This one goes from 2 to 0. +6. Well, guys, I'm going to have to look this one up a second. I must have made a mistake in assigning the oxidation numbers. Oh, it goes from 0 to -2. Oh, I'm sorry. Yes, this is on, I'm looking at the same side of the reaction here. This side of the reaction here is 0, and it goes to -2 over there. Thank you very much for posting that up. I was looking on the same side of the reaction. That's my fault. And this one goes down right here, and so it's reduced. My bad. I was looking at this one changing to something on the same side. It can't do that. It's got to change from this side of the reaction to this side of the reaction. So thank you for pointing that out. I was just looking in the wrong place. This one goes from 0 to -2. It goes down and it's reduced. This one goes from -2 to +4. It goes up and it's oxidized. Thank you very much for pointing that out. Which other ones would you like to see from, should we do 52C? Should we do some from 51? Number 51 is the request. Okay. Any particular ones there, or just start? We'll just start with letter A. N2 plus 3H2 goes to 2NH3. So this is alone by itself, so it's 0. This is alone by itself, so it's 0. And then over here, using your rules, hydrogen's +1 when it's with a nonmetal. Nitrogen is a nonmetal right here. And then hydrogen, of course, this way to add up to 0 would have to be -3. So now we can see nitrogen goes from 0 to -3. It went down in charge, therefore it's reduced. And hydrogen went from 0 to +1, so it went up, and it is oxidized. All right, that's 51A. 51B, this one's got Fe and then NO32 and then 2Al, and it goes to 3Fe, and then it's 2AlNO33. Pick out the easy ones first. This is 0, this is 0, because they're alone by themselves. Another easy way to do this one is to recognize, oh yeah, this is nitrate. Nitrate's -1. I memorized that. And nitrate's on this side too. It's -1 as well. Since they don't change, that's not going to be the thing that is oxidized or reduced. And they're not saying assign oxidation numbers for everything. They're only saying which element is oxidized and which is reduced. Since these aren't going to change, just ignore them and just say, oh, they're going to be the same. But since this is -1 and there's 2, iron would be +2 here. And since this is -1 and this is 3, aluminum would be +3 right here. And now you know your things that changed. Iron went from +2 to 0, so it went up in charge and is oxidized. Aluminum went from 0 to +3. I'm sorry, I said this wrong. +2 to 0 is going down in charge, and so it's reduced. 0 to +3 is going up in charge, and that is oxidized. Up and down are sometimes backwards here after doing this stuff for a little over an hour. Thank you very much for your patience. Should we go on and do C? All right, we'll do C. So C is Cl2 plus 2NaI. I'm just going to ignore the 2 because that's not going to be part of assigning oxidation numbers. I2, and then we've got NaCl over here, and I'm going to ignore the 2 once again because that's not part of assigning oxidation numbers. So pick the easy ones first. Chlorine's alone by itself, 0. Iodine's alone by itself, so 0. Sodium, that's a group 1 element, right? And group 1 elements are always +1, 99.9% of the time. Okay, so +1, that means iodine must be -1. Over here, sodium's +1, that means chlorine must be -1. And now I know the things that change. Chlorine goes from 0 to -1. That is going down in charge, so that's reduced. And iodine goes from -1 to 0. That goes up in charge, and therefore it is oxidized. Is that enough, or should we do D? Do D. Okay. PbS plus 4H2O2 arrow PbSO4 plus H2O. I'm going to ignore the 4 right now. Ignore this 4 right now because it doesn't matter in oxidation number assigning. This is a good one because it's got a tricky part to it and you have to make some guesses. Hate those kind. Oxygen here is -2. That means hydrogen's +1 because it's with a nonmetal and it adds up to 0 up here. SO4, I've seen that before. That is a polyatomic ion that I memorized on the back right here. It's called sulfate. It's -2, which means that lead right here must be +2 to balance out this -2 species right here. Okay? Now I could break this up. SO4 is -2 overall. Oxygen is -2 with nonmetals times 4, -2. It's going to equal, what does sulfur have to be? Something plus -8 equals -2. That means sulfur is +6 on this side of the reaction right here. Over here on this side, sulfur and lead. Now, you don't like this, but you're going to have to make an educated guess. Lead is right here. Oh, I don't know. Sulfur is right here. The more electronegative one is actually sulfur, which you'll learn about later. But it's the nonmetal, and so we're going to guess that that's -2, which is a pretty fair guess as long as it's with a metal, and lead is a metal, and so that means lead would be +2 right here. So notice lead doesn't change, but sulfur does. It goes from -2 to +6, so sulfur goes up in charge, therefore it's oxidized. Last one, I saved this one for last because this is the trickiest. Notice it's H2O2. O2 is what's called the peroxide ion. The peroxide ion is O2 -2. It's on the back of the periodic table right here. It's the one exception for where oxygen is -1. Hydrogen with nonmetals, of course, is +1. And now we know our second species that changed. Peroxide oxygen atom here went from 1 to -2 right here. And so it went down in charge and it is reduced. All right, that's all of 51. There's only a couple of you left on the chart right here. Do either of you have any other questions, things you want me to go over? Okay, I'm going to stop the video now. I'm in 1 hour and 7 minutes.